All right. Hi, everyone. I'm Ashlyn. I'm in my third year working with Dr. Khetani in the microfabricated tissue models lab. We have quite a lot of different projects, but they all fall under the umbrella of tissue engineering, and I'll give an overview of them today. So next slide, please. We primarily engineer liver and cardiac tissues, but we do have members with projects engineering intestine, placenta, pancreas, and blood. And our projects focus on creating the optimal conditions for an engineered tissue. This includes which cells do we choose to use. We can use primary cells either from human, mouse, or rat sources. These can be the most in vivo relevant, but they can be quite difficult to obtain in large numbers and also very expensive. So we also work with stem cells, which allow for the benefit of personalized therapy, though they also require lengthy differentiations, or cell lines, which are maybe cheaper but less relevant. The other question we ask is, what environmental cues do we include to maintain a stable phenotype? And this can include everything under the sun, including biomaterials, which incorporates things like stiffness, biocompatibility, extracellular matrix coding. We also incorporate micropatterning, microfluidics, electrospinning, and many more techniques that aren't listed here. And all of these choices are informed by what we want to do with these tissues. For instance, we have projects in disease modeling for hepatitis B infection, alcoholic or non-alcoholic fatty liver, atrial fibrillation, preeclampsia, probably some more that I'm forgetting too. And we do drug screening to predict metabolism and toxicity in models relevant to human health and also in multi-organ models. And we're also working, we're also working on cell-based therapy projects, for instance, hematopoietic stem cells for bone marrow transplantation. Next slide. So on the left, we have examples of our cardiac models. We have micropatterned co-cultures of cardiomyocytes derived from induced pluripotent stem cells surrounded by supportive fibroblasts. We use this system to mature these iPSCs, which are usually immature when you first make them. And we have examples of some of the analysis we do. We immunostain and look at the sarcomere length to assess maturity. And we also do optical voltage mapping to assess electrophysiological characteristics. As you can see, the cells here are flashing as their voltage changes, and we can use the intensity of this flashing to calculate action potential duration and amplitude. And on the right, we have some of our liver technology here, the generation of microfluidic droplets of hepatocytes or liver cells embedded in a collagen matrix using a microfluidic device. We make these hepatocyte microtissues. I didn't realize that video had audio, but you can see the microtissues being pinched off at the T-junction by oil flowing through the perpendicular. And after we make these tissues, they're liquid at cold temperatures, and then they polymerize at warmer temperatures, and we can coat them with supportive cells. And we recently obtained a confocal microscope, which my colleague used to take this beautiful picture of a coated microtissue in the bottom right. And this is our lab. We have people from all over the world. I think Brazil, Sri Lanka, China, Nepal, India, Mexico, Korea, Italy, just all over. And we really prioritize diversity. And I think this reflects UIC as a whole. We also have several alumni that we've placed in pretty top tier positions, both in industry and academia. And we have a lot of connections in industry and academia as well, and a lot of collaboration.